Unit 9, what we're crash course doing, is it covers applications of thermodynamics. So in Unit 7, we did talk a lot about thermodynamics. We talked about enthalpy, which is the delta H. We talked about heat, those kind of things. So, and we, like in Unit 7, Section 14, we introduced the terms entropy and Gibbs free energy. Okay, so entropy is something that refers to dispersal of energy in matter. Okay, so when we're thinking about if something has a higher entropy, it's like gaining entropy, or if it's losing entropy, similar to like heat. What we're looking at is when is it more ordered and when is it more disordered. So that's what the dispersal means. It's just like if it's getting farther apart, that's dispersing, so the entropy would be increasing. Okay. So considering our phase changes, like if we were to go from a solid to a liquid, the particles are going to disperse a little bit more. So that would be a gain in entropy. And then the same thing if you're going to go from a liquid to a gas. The gas particles would disperse even farther. So then that would be a gain in entropy too. So like if you had a value, just like with enthalpy and endothermic and exothermic, if you are gaining entropy, you'd have a positive sign. And if you had a negative sign, that would mean that you're losing entropy. So this is just an example with phase changes. So again, if you're going from a solid to a liquid, as you disperse more, you would gain. If it's the other way, if you're going from a gas and condensing to a liquid, you would reduce the entropy or lose it. So then it would become more ordered. That would be negative. All right. Okay. Like I said, I am recording this, so don't feel like you need to scribble everything down, because I know that we like normally have guided notes and we just don't have this today. Okay. Whenever we're looking at chemical reactions, gases are the best indicator to know if we're gaining entropy or losing entropy when we're looking at the reaction. Because with gas particles, they're going to constantly move around, and if they can spread themselves out, they will. Okay. So when we're looking at gases, particularly and considering with volume, when you increase the volume, you're able to increase the entropy because there is more space for the gas particles to spread out. Okay. So that's what this picture shows, is that if you had a container that had a wall in the middle, you were able to remove that wall so that the gas particles were able to spread out even more, then that would cause an increase in entropy. Or if you were like to condense the volume down, then that would be a decrease in that. And so like for chemical reactions, anytime that you have gaseous reactants, then the entropy will generally increase. And it has to do with the moles of reactant gas versus moles of product gas. Okay. So I have two examples, one where we only have one gas present as a reactant or product, and one where we have all gases present. So if you are, for the top one, this is potassium chlorate, solid, that's decomposing into potassium chloride and oxygen gas. Since there is oxygen gas on the product side, this would be a positive entropy case, because as the reaction progresses to the product side, we are creating gas, which will be able to be dispersed better than solids, because all of the solid molecules would like to just stick together, the particles to stay together. So it's really, really easy if you look at a reaction, if you only have a gas on one side. You just always say, like the forward reaction, it would have more entropy on the product side because of the gas on the product side. Okay. When you have all gases, like this is the combustion of pentane. If we have time before the exam, we'll cover organic things. You don't have to know them, but you don't have to know them, kind of thing. They don't really have standards about it, but they are included. So anyway, when you combust pentane with oxygen gas, then it creates carbon dioxide and water, combustion reaction. Okay. When you have all gases present, then you just count up the moles. right? So you use the coefficients to see which side has more, and the side that has more would have the higher entropy in that situation. So for the reactants here, we have 1 plus 7 to have a total of 8. You guys need me to write that down? So this was the 1 plus the 7, so that's a total of 8 moles of gas on the product on the reactant side, and then 3 plus 4 is a total of 7 moles of gas on the product side. So if we're just thinking about this reaction and which side of the reaction, reactants or products, would have a more favorable entropy, that would be the reactant, because the reactants have more total moles of gas involved. We've done that a little bit this year where we've looked at the coefficients and figured out with gases what's happening there. Not only with gases, you could also, if you have solutions or liquids, that would have a higher entropy than just a solid, because the solid particles are not going to move. But if they're liquid, or if they're aqueous, or if they're gaseous, then they will have a higher entropy, sort of thing. Right? Does that make sense? Look for the side with more. It's like opposite thinking when you think about numerical values, because when it's more entropy, it's actually more crazy, but that's how that goes. Okay. Now our textbook, so this is in chapter 17 of our textbook. And most textbooks like ours, they use the word spontaneous to describe entropy. And this is something that we're trying to get away from, because anything can be spontaneous. A spontaneous reaction would just mean that it's going to happen, right? And like over time, a car will begin to rust if you don't take care of it, if you don't stop the reaction happening. So spontaneous reactions will just go by themselves. They might be fast, they might be slow. Like if you try to let a car rust out, it's going to take a long time. But we do have some chemical reactions that are very quick as well. And then the non-spontaneous would be like, for this example, going backwards, or sometimes you have to add like an energy source in order for that non-spontaneous reaction to happen. You guys remember when we talked about activation energy this year? Like activation energy is the amount of energy that you have to put in order for something to happen. It's like that barrier you have to cross. If you don't have enough energy, it won't happen. That's the same thing with spontaneous, non-spontaneous reactions. So if you're trying to describe something to say that this would have more entropy or less entropy, it's suggested that you don't use the word spontaneous, because in our textbook, if you look in that or you look online, you might see the description say that when it has more entropy, it's going to be more spontaneous. And because spontaneous reactions, like the terminology, they don't like it. So they would prefer that you talk about not the spontaneous versus less spontaneous. They would rather you say like more dispersed or less dispersed. So if you use the words like spontaneous and you're trying to describe something, you might not get the point for your justification for your response. So just be careful with that. Okay. Okay. Kinetic molecular theory, we talked about this a long time ago. Kinetic molecular theory just talks about how like molecules are going to move, and it correlated kinetic energy directly related to temperature. So if you're at a higher temperature, you have more movement than if you have a lower temperature, right? So with entropy, it makes sense that if we know at higher temperatures molecules move more, then there's a higher probability that they'll be dispersed. So then at a higher temperature, they probably will also have a higher entropy kind of thing. So I think that's what that's covering. Yeah. Okay. Well, that's the answer. So looking at this equation where we are producing ammonia, okay, we want to predict the change in entropy. So change in entropy would be like final minus initial. So we're going to predict if we had done numerical values, which we don't, would it be a positive change, meaning that it's going to become more dispersed, or is it going to be a negative change because it started more dispersed at the beginning? Okay, so looking at this, we have a total of 4 moles of gas on the reactant side. We have 2 moles of gas on the product side. So we already know that the entropy will be higher. It'll be more dispersed on the reactant side, correct? So an entropy change value would be negative because as you produce, you are producing less molecules overall of gas, okay? And so you could say something like about the moles of gas, and then to make sure you hit the point home, you could say that with less moles of gas in the product, the dispersal of matter and energy in the product is less. So just trying to use that dispersal terminology when explaining yourself. It's good. Okay. So how do we feel about that so far? Not too bad. Not too bad. Okay. Just like with enthalpy stuff, there are numerical values associated with this. If you look in the packet that I gave you, let's just look at that really fast. I don't have anything else here. That's what I covered mostly. So, oh so this in model 1 in this table, it's talking about all these different processes. So some of them are just physical changes, some of them are chemical changes. And so just like how enthalpy, we could say that, like, you know, it would be positive, so it's the endothermic, it's negative, so it's exothermic. We can also assign like increasing entropy or decreasing entropy as well. Okay. Now, with those, they get related. If you go to page 3, I think, no, page 4. Yeah. So there's this equation on page 4 that is the D is called free energy or gives free energy. And so this actually relates together the enthalpy, the heat information, with the entropy information, where you can predict what's going to happen for a reaction, if it will spontaneously happen or not, using values for all of this information. T here is just temperature, but then the change in enthalpy is delta H, and the change in S, or the delta S would be the change in entropy kind of thing. And so tomorrow we'll talk a little bit more about how the free energy is related in this way. And so some situations where we might have information about the heat and about the entropy and see what's predicted to be spontaneous or not spontaneous. Okay, so that's what I got for today.